Alright guys, so if we turn this sucker over, look at all that. Uh-oh. Now if you borrowed a calculator, you probably just got very lucky, because we did this in my early class. So you probably already got all the data in here. Yay, so do I. So,
Put it in?
put this data in. If you weren't here last time, so we're gonna do, and even if you were, we're gonna do a little review of what we did Monday. So go ahead and put this into list 1, this into list 2. By the way, does this data really matter in our analysis?
No.
No, it only matters after our analysis, right? In the homework, you'll see some where they give you years, and then I don't care about the years, right? Anyway, you'll see. Oh shit. Do I have any more? Oh, I'm in the wrong thing. Alright, let's see if we get lucky. There's one that already has it in there. I do. So, just in case you missed it, we are gonna have a quiz on Monday on this stuff, linear correlation stuff. You're gonna come up and show me your scatter plot and your line of best fit. I will help you if I notice something's way off, right? Because this is horrific. I'm sure you guys understand. You guys ever seen like make money from home, college students over summer?
Yep.
That most of those are data entry jobs. Because make college students do it. We hate doing it. They'll do anything for money. Yay. So maybe, well, do it if you want to. It's good money. Okay. But I would kind of double check these when you put them in. Let's see if this looks right. Yes. Now let's see, you guys are close to done. Get it all in there. Let me ask, why would this be possibly a silly thing to study? This is kind of an easy, by the way, this is all real, this is all true, probably about 10 years ago, because, you know, I'll make a worksheet and then I'll use it over and over again. But real quick, why does this just make sense that there would be a correlation between these two sets of data? Anybody? Why would it make sense that the percentage of people with a bachelor's degree in a state might have some relationship with the median income in that state? Yeah, higher paying jobs require more advanced degrees, right? But think about it this way. Could it be true that to some extent, if there are better paying jobs, people have money to actually go to college?
Yes.
Ah, so the first thing is probably more of what's going on. But we don't know to what degree it's actually the second thing, right? So that's, even if it's kind of obvious, it still isn't as obvious. I don't know what's causing what here and to what degree. Are you guys sort of with me on that?
Yeah.
Okay. At least one person. All right. So, if everybody's got all the data in, can somebody remind me, because I forgot how the hell to do this, what do I push to make this calculator do its magic and tell me, by the way, what two things do I want to know?
A, B, and R. Y and R.
Be less specific. What two things do I want to know? I want to know the correlation coefficient, which tells me what? What is the correlation coefficient now? What's the variable?
R.
R. And what's it tell me?
Like the relationship between
The
the data and the correlation.
I love it. It tells me how strong the correlation is, right? Visually, it would tell me how tight the points are to the line. The closer R is to what? The closer R is to what? One, the more perfect it is. The more perfectly the points line up, right? As you get away from one, they start to spread out. Negative one is also perfect. It's just a negative slope, right? I'm trying to think from your perspective, what would a negative slope be? This, okay. All right. So we want to figure out the correlation coefficient, and we want to figure out what else?
Line of best fit.
Line of best fit. So, real quick, I said this last time, but I kind of like this analogy. Bless you. Every time I gave us new data, a new way to give you data, when we had a list of data, when we had a binomial distribution, when we had an XP of X, we had to figure out a way to figure out the mean and the standard deviation. The line of best fit is like a visual mean, and the R is like a two-dimensional standard deviation. It's a neat analogy. Does that help you do any problems? No, I'm sorry. But it's a nifty idea. So, now help me. Those two things. What do I push to make those two things come out of this expensive little dude?
Right.
Stat. Calc.
Four.
Yeah, so who remembers what that stands for? LinReg? Linear
regression.
regression, I love it. Right, it's just the technical name for this process we're using. Linear regression. There's also 8 to screw it. We'll do 4. You can use 8 if you want to, it's just silly. By the way, if you have a calculator that's got an older operating system, you'll just see LinReg. Just hit enter, because it defaults to list 1, list 2. If you get all this shit, then we gotta go through all this shit.
Sorry, I'm just gonna grab that.
Oh yeah, sure. You need a, you're good? Okay. All right, did everybody get this? Wait, it's coming back. There it is, okay. Did you guys get those numbers? Did anybody get those numbers?
Yes.
Yes. Okay. Did anybody not get those numbers?
Mine doesn't show R squared and R.
Ah, okay. Anybody else in that same boat? Anybody else only getting A and B? Right? Well, unfortunately, you got the wrong, no, I'm joking. So, you didn't pay enough money for that calculation. If you're not getting the R to show up, do this. You only have to do this once, right? See this right above the 0? Where it says catalog? Hit second 0, right? So if you didn't have R showing up, do this with me real quick. Everybody with me that needs to do this? Hit second 0, and you get this showing up, right? Then I want to go to the section of the list that's in the D, so I want to hit this button that's got a D on it, right there. So now I'm in the D section. And then I want to scroll down to diagnostic on.
Can you show me where the other?
Hit second 0, and you get to catalog.
Yeah.
Hit the, see the little button there with the D right there? Right above it, so it's this button right here. Hit that, bam, then it should be here. Kind of freaky, your calculator will actually tell you the day of the week if you input the right stuff. We don't care about that right now. Whee! Are you with me? Diagnostic on, go down to diagnostic on. Yes, maybe. And then hit enter. Enter. Enter once to tell it what you want to do, and enter again to make it do it. Right? And then, oh, go ahead.
For some reason mine doesn't show, so I was wondering, once you have it on the list, you said you go to calc, right?
Yeah.
So like I have my list, right?
Sure.
And then go to stat, calc, and then form.
Yeah.
And then I gotta switch anything on that?
Yeah, the freaky list. Make that empty. Hit clear. Okay. Is it cleared?
Yeah. And
Okay.
then-
Now. Oh, this is one of the worst. Okay. That sounded terrible. Dim mismatch means your lists are not the same size. You lost somebody. See there?
Oh.
That sucks. So, guys, here's a common. By the way, real quick, if you are going along with me, this hit stat, calc number 4, do you now have R showing up?
Yes.
Everybody, that didn't, okay. Okay, so, I'm gonna do something, never do this. I'm gonna take out this last element.
No.
Poor little dude. Now, if I go to do stat, calc, lin reg, look what it's gonna tell me.
Wait,
Dimension mismatch, right? Any damn time you have a go-to option, right? Not Goku, sorry, it doesn't work here. Go-to, you wanna go to, because it's gonna put the cursor on the problem. I'm curious, I don't know if I've ever done that. Oh, so it's telling you there's a problem in list 2. That's not very helpful. So if I go to edit, and I look and I say, oh shit, so dimension mismatch. The length of one list is not the same as the length of the other. That's a mismatched dimensions, right? It's like one piece of lumber is differently sized from the other. That's dimension mismatch. So now what the hell is that last dude? 65, 358, yay. Okay, real quick. Can somebody tell me, is this strong or weak?
wrong.
Shit, yeah. It's a decent sized sample too. So what does that mean? Well, it means that the threshold for correlation would be a little lower. So the fact that it's freaking 0.924 is silly. Is it positive or negative? Positive. Never look at R squared for that, because R squared is always going to be positive, right? Always look at R for that. And what's the line of best fit? What's the slope?
It's
1570.74x,
B over O.
12,231.
Yeah. So A is the slope, B is the y-intercept, right?
C
Okay. What are the units on the x variable?
Percent.
Yeah, here's the x's, correct? So isn't the x variable percent with a bachelor's degree? Right?
Yeah.
It's xy, just a normal xy table. So there's the x's. What are the units on the y's?
Dinero.
Money. Yeah. So this slope is money per percent. So it's sort of like every 1% increase in the number of bachelor's degrees held is a $1,570.74 increase in median income. Let me say that again. Every 1% increase in bachelor's degrees held translates to a dim 1570.74 increase in median income. Now, real quick, the way I said that is a little misleading, but I've got to say it one way or the other. That kind of implies causation, but again, we don't know if more degrees causes higher median income. It's just observation. We didn't do an experiment where we made people get more degrees and then we looked at the median income after. That would be a causation experiment, yeah.
So you said with every percent that would increase,
By 1570.74, the median income, yeah.
it's not 1570.74 plus 12,231?
No, that would be what the median income is. I'm saying how much would the median income change if I change the percentage by 1?
So B is the median income.
No, B is the y-intercept.
But doesn't that factor into the?
If I wanted to know what the actual median income was, I'm asking how much does it change if I change the percentage of bachelor's degrees holders by 1%? Yeah. Yeah.
What's A?
What's A, everybody?
Slope up.
Yeah. How do you know it's slope? Because it's in front of the good old mx plus b. So, these are statisticians. So, of course, we changed the letter M because, those silly math people. Of course, I'm both, so what the hell? Gotta hate myself. Okay. By the way, guys, what's slope? Can somebody tell me words for slope? Something. Rise over run, right? So normally if I had a slope of 3/5, that would mean I go up 3/5. Does that sound familiar? For you guys, it would be up 3/5, right? Is that cool? Is that cool? 1570.74, is that a fraction? No. What is it over? 1. Yeah, anytime you have some numbers not over, it's over 1. So it's percentage of bachelor's degrees holders over money. right? Or this is the other way around, now I forgot. It's money, there we go. Y over X is my slope. So it's median income per percentage holding bachelors. So 1570 is how much the median income changes if the percentage of bachelor's holders changes by 1. So that's the number on the bottom. Okay. All right. So there will be a couple of homework problems that ask you to interpret the slope. Just look at the units. Slope is always y over x. So you just look at the units in the second column over the units in the first column. That's the slope. That's what the slope represents. Okay, so let's try to get this to show up in our graph. So let's write some shit down. Y equals 1570.74 x plus 12231.47. Looks like, okay. Just trying to get 3 for what we do. R was
0.9238.
I like it. So pretty strong. Now, wait a minute, here it is. I did give it to us. So it had to be greater than 0.482 to show evidence of correlation. Blew that sucker out of the water. There's evidence, and not only is there evidence, it's pretty strong. Interpret R. When I ask you to interpret R, I just mean your answer could be it's a positive, a strong positive, it's a weak negative, it's a strong negative, you know, whatever. So this would be, like we said earlier, this would be a strong positive. Strong positive correlation. What does that mean for the line of best fit? There's 2 answers you can give me here. What did we say earlier about R? It's the strength of the correlation, which tells me what? About the line and the points.
How close they are
Yeah.
to the points are to the line.
So in this case, what does this R tell us about the line of best fit? It's the data points, Sure, Jeff. Data points get really close to the line of best fit.
So is it R the closer it is to 0 is strong correlation? Or
Should
I was-
know.
No, I was
What's R equals 0 mean?
That means there's no slope.
No linear correlation.
So closer to 1.
1 is strong, is perfect positive correlation. -1 is perfect negative correlation. 0 makes sense that it's no linear correlation. I like it. I like it. So one way you can answer this question is the data points are really close or tight to the line. That's the way I like to say it. Another way to answer this question is would we trust predictions we make with this line?
Yeah.
Hell yeah. It just needs to have correlation, but this has like strong correlation, so I'm gonna trust the shit out of its estimations. Okay, whatever that means. So put that down, trust the shit.
Wait, the 1 in 0.48, it'd be a positive correlation, but why is it a strong correlation, like compared to like 0.8? Like, wouldn't 0.8 be stronger?
No. 0.924 is strong. 0.924 is strong.
Right.
For the size of our sample, I had to get greater than 0.482 to show evidence of any correlation. So if our R had been 0.49, that would have been correlation, but it would have been really weak. I would still trust the line more than just guessing.
Okay, yeah.
If R was less than 0.48, no correlation, I don't trust that line.
Okay.
I like that reaction. Okay. So now I can actually make a prediction, because we're gonna trust it. Real quick, this is something that's new for us. Did everybody, hopefully everybody just left these numbers the way they are? Okay. That means that we built this freaking equation ourselves. We don't have to change percentages into decimals, because we built it to work with percentage numbers. Are you guys with me? So part of me loves it if somebody actually makes this 0.376, because that's what your sign is generally supposed to do. But we created the equation to work with percentages. Does that make any sense? I want that to make sense. So we could just throw the whole freaking thing in there. So I've kind of given away the game. How do I predict for a state with 37.6%?
You put that into the, you put that in.
Plug it in where?
X.
For X. Kick X. Yes.
71,291.29.
You know where it says y equals?
Yeah.
Whenever it says y equals, where it says r equals?
Oh, come
stats, my pre-calc class was doing some extra weird shit with this. I'm gonna plug it back in, but I got your Y's back. Alright, so let's take a look. You guys, so real quick, has anybody done that yet? Just shove the 37.6 there?
Yeah.
What do you get?
71,291.29.
Alright, all that crap. Okay, so if I go back to my graph, oh shit, we haven't graphed it yet. How do I, alright, I just hit graph. I forgot we hadn't graphed it yet.
Do you see any of my data?
Oh.
No. What did I forget to hit? Anytime I have new data, I should hit zoom. Zoom. 9. For most of us, it should be 9 for zoom stat. So let me know if this does not show up. Now my line of best fit, I haven't changed it from last time, so I still have to go back to y equals. Is anybody not seeing their data?
Mine shows as like the boxes.
Yeah, the boxes are fine. That's what I normally am. I feel weird not being a square. There I am. Magenta? Sure. That's me.
So grab zoom 9.
Zoom 9, yeah. If that does not work, do this. See above y equals, it says stat plot. Hit second y equals. Is everything turned off right now for you?
Yeah.
Alright, hit number 1. And then hit enter when you're on top of on. And then everything else should look like this.
Okay.
Now when you hit zoom 9, you should get that.
Yeah.
How do I make the line of best fit show up?
Trace.
Nope. I don't have it in there yet. How do I make it show up? What do I do? Yeah. So to make the line of best fit show up, it's kind of nice. I just go to y equals. I've got the one from before in there, so let's clear that out. 1570.74 x plus 1223 1.42. Is that what this is? 47? Is it 7?
47.
Thank you. The most common mistake is people forget the x, and then you just get this straight line, and normally it doesn't even show up on your graph. So don't forget the poor little x, dude. So now when you graph, it should look like that. Maybe less colorful, I don't know. What, can somebody tell me really quickly why that looks correct?
Because the data points are close to the line.
Yeah, especially down here. Look at that shit. But more importantly, how do you know it's not too high or too low? Because the points on either side sort of balance each other out. Do you see that? Now again, that's an extra thing. That's an extra thing. But if it was way too far up, that would be really obvious. This is like got equal numbers above and below it, so it feels like it's averaging stuff out. So that's what it's supposed to do. Yeah.
See what I mean?
Outlier.
When it puts in stat, it does.
Neato.
That's what I meant.
I got you. I'm sorry. So what happened is somebody set it to be histogram. You want to set it to be scatter plot. Holy shit. What is that? Oh, so somebody's doing some weird stuff. Does that say R? What does that say? Y?
Yeah, one.
Somebody put some weird stuff in there. So you need to put,
Yeah, but.
oh, it's not clear. There we go. You need to put the equation.
Oh, and then how did you put the X in there?
There's your X button right there.
Oh, okay.
Yeah.
Thank you.
Mine is also. It's not.
It's doing what?
It's making a weird sound. It's not the one we were looking for.
Alright, let me catch up to you. So you got all the stuff in there. So you want this first one highlighted. Enter.
This you just leave.
So now hit zoom 9. Zoom 9 is zoom stat. Kickass. Now all I gotta do, all it's missing, oh no, something went wrong with your y equals. Oh, what's it say? Syntax. Okay, so go to. Yeah, you got extra stuff for some reason. So clear all this stuff out. Whee! And there, that looks, oh, you're missing one number over here. I think it's 12,231.47. 12,231, I think is what it is.
Okay, everybody else all right? So on this quiz, what you're gonna have to do is, this problem I give you, you're gonna have to come up and show me this.
Yay. So like, is the entire quiz just us getting to that point, or?
For the most part, there'll probably be two problems. One is gonna be this, and the other is gonna be a quick little question about, I don't know, correlation, causation, or something.
What you guys did Monday?
Huh?
What you guys did Monday?
Yeah, part of what we did today.
Can you show how you got the line again?
Yeah, y equals. But how did I get the equation?
Oh no, that, and then just as soon as you hit equal or
Zoom 9.
enter.
Shabam! Yeah. You can use whatever sound effects you want. You guys okay with that? Now, my experience tells me normally students really like this, especially compared to hypothesis tests.
Oh,
Yeah.
Relatively, this kicks ass,
Way better.
right? Okay, good to hear. We'll see how you guys do. Alright, what about the last question here? Oh, did we finish this one out? I'm sorry, I was gonna show you something neat. Remember this, if you hit second trace, you can calc. This entire first row is graphical stuff. So if I go to calc, I'm gonna calculate something graphically. I wanna calculate the value. I wanna calculate the value when the input is 37.6. So is this what you guys got? Is this your card? Where'd he go? 71,291? Yeah? Why do I say compared to Virginia? Because you're weird, Jeff. Why do I say compared to Virginia?
Because that's the closest data point.
What percentage of bachelor's degree holders does Virginia have?
37.6.
Yeah, so did we just calculate for a theoretical state that has 37.6?
Yeah.
So then let's see, how close did our prediction get?
Pretty close.
Pretty close. Why was it close? Because the correlation is strong. Why was it not exactly?
It's not one.
Because it's not perfect.
Close.
Yes. It's imperfect stuff. Yes.
Wait, how did we get that number again, sorry?
Oh, this one here?
Yeah.
So one way you can do it is just take this equation and plug 37.6 in. Because these are the x's, these are the y's, right?
Yeah.
Okay, these are the x's, these are the y's. What I did was I just made the calculator do it, but
Oh.
you can do it either way, yeah?
So this is a good question someone asked is, when you type in the percentage, like into the equation, you know how we normally convert percentages into decimals?
That's what I just said earlier, so it's,
Oh.
we created this equation based on these numbers, and these numbers are percentages. So since we created the equation, we made it accept percentage inputs. If we had put all of these in like 0.281, 0.348, if we had made it based on on decimals, we would have had to have decimal inputs. Does that make sense? You guys don't get to create your own equations very often, so you're not used to being able to do that shit. Okay.
How come when I put the decimal, I got a different answer?
Oh shit, yes. If you put 0.376 in, that is 0.376%. That is a state that less than 0.5% of its population has a bachelor's degree. That's not what it's asking, right?
Yeah.
So that's exactly what we're talking about. You don't have to make it a decimal because we didn't make the data decimals.
Yeah.
The inputs can be percentages. In fact, they have to be percentages. Does everybody get that? If I would have taken a second and made the X column 0.376, 0.272, then I would have had to have decimal inputs. We created the equation, so we just do what we created it to do. Maybe. Maybe? Okay. All right. Last question. Do your results mean that if you suddenly somehow got more people to have a bachelor's degree, that the median income would go up?
Yes.
No. No. Nope.
Oh.
Nope. What of a state, just to show you why, because number one, hell no, never. When I ask that question, the answer is no. Does that mean that it wouldn't go up? No. I don't know what would happen. This analysis just says there was a relationship. It does not say what causes what. It could just be a coincidence. So changing one does nothing. How about a state, real quick guys, why did we say
that a higher percentage of bachelor's degrees makes sense to translate to a higher median income. Why did we say that?
We're assuming that a job would hire you because you have a degree.
Yes, so there's jobs that require advanced degrees. What if there's a state that had very, very, very few of those jobs? Getting a bachelor's degree, would that help somebody? No, unless they got lucky and got one of those very, very few jobs. Do you understand? So then if I had that kind of state and I made more people get bachelor's degrees, I wouldn't see much of a change necessarily. Do you guys understand what I'm saying? So this analysis can never, ever answer a question about what causes something to change. It can just tell me, what do I see right now? It's a snapshot. Okay, maybe.
So what do we write?
Because right
What
now,
do we write?
We write no. Does it mean that if no, why or why not? Because correlation does not imply causation.
So any
Now, real
question-
quick,
Any question we see like.
There could be, it totally could be true. In fact, using our life experience, it makes sense that there would be a cause. But this analysis by itself does not tell us that.
You have to talk about the correlation in your answer.
Say again?
You have to talk about the correlation in your answer.
Yeah, you have to say something about it, right? I mean, how did you
Just
answer?
go Look at Wyoming and Ohio, because it shows that it's false.
Oh, I see. Now again,
It could just be different.
Again, that's a snapshot. So somebody would argue, no, what if I go in and give more bachelor's degrees to the people there? Right? The trend is showing that it should go up. Now that's a misinterpretation, right?
And also-
I know what you're saying. They buck the trend, they're outliers. But that still doesn't say necessarily that it wouldn't go up if I increased the bachelor's degrees, right? Okay. Yeah.
I was gonna say, because also like there's other factors like that, like every state has different economy, so, and all that.
Yes. And by the way, real quick, Ryan, one reason why that's not a good answer is because what if there were no states like that? It still wouldn't mean that. Do you see what I'm saying? Okay. So it's a broader idea than just that kind of thing. Okay. Yeah.
It's kind of like it's evidence, but it's not proof.
Yeah. Yeah. Sure. Yes. Totally. But you have to do a completely different analysis. So, guys, can we do a statistical analysis to see if a certain drug works better than another drug?
You.
What would we do?
give them drug. But then it's all these factors.
True, but we would get, basically what we would do is we get one group and give them the drug, get another group to give them a placebo, right? Okay, I like it. See some people back there saying we're gonna get drug. No. You guys with me? So that would be an experiment to see if there's any causation. I love what you just said. There's a lot more to it than that. There's controlling for other variables, all that kind of shit. But just on the surface level, that would be seeing the cause. What was different? Did we do anything here? We just went and looked. Did we actually go in and start doing something? No. So if I wanted to see if this was a causation, I'd have to actually go change something. I'd have to apply some treatment. Does that make sense? That's the kind of experiment that would lead to an understanding of what's the causation. All right. I think you guys all understand this, that in an early math course, this is stats 1. This is the first stats course, correct? There's a lot more to the story. There really is. But nothing I'm saying is incorrect. There's just a lot. The correlation can be used to tell you some stuff, but you have to do a little more stuff after what we do. So we're not there. Okay, that's all.
That's right. Correlation does not cause.
Correlation doesn't tell you anything about causation. And causation is which thing causes the other thing to change. You with me? Now, again, something simple like how old a kid is and how tall they are, we know that the age does. Now, does that mean across the board? Is there anybody that just stops growing at some point? Yes.
Yes.
Is there anybody that actually doesn't grow at all? Yes, that's happened. But as a general trend, we've observed that enough that we feel pretty strong that that is a cause, right? Getting taller doesn't make you older. Getting older to a certain age makes you taller, or lets you get taller. Does that make?
Yeah.
Okay, but that's got a lot of observations behind it to back it up. Are there other variables that affect your height?
Yeah.
Hell yeah, right? Got a lot of stuff that can stump your growth, right? Okay. That went further than that. So this question is really easy to mess it up, and I understand because we're just human, right? But the answer is actually, a great answer would be, I don't know. Because we don't know. This is not the right kind of study for that. This is just a snapshot. Okay. Maybe. Okay, so this is basically gonna be the quiz on Monday. Okay. Not exactly this, you know better than that. Anything about that before we move on to today's stuff? Okay. So today, this is one of my favorite things. We'll see what you guys think. Poor little dude. There you go. That's better. Crap. This is the most exciting part of class. Okay. So guys, see if this brings back any traumatic experiences. Do you remember when we went to alternate universe Florida in our imaginations? Okay. See a few pained examples, a few pained expressions. Do you remember the whole premise was I walked around and talked to people, and what did I do? Does anyone remember what the hell I was doing? Yes. And then when I plotted it, it was all freaky. When I took a sample greater than 30, right? So when I took a sample greater than 30, and I asked a group of 38 or whatever it was, and I said, what would I ask them for? Their average age, right? Their mean age. You guys with me? So I go around, I go to the first group and say, okay, you, what's your average age? 83. Okay, so then I would go and I would plot 83. Then I go to another group. What's your average age? 11. Okay, what's your average age? 47. What's your average? Blah, blah, blah. And eventually, over time, what would it look like if I got everybody in the entire population plotted? It's got to be normal. Why has it got to be normal? Because it's greater than 30. And again, if I have a, let me see, if I have a sample of size 38, does that sample have to be normally distributed?
No.
Good. No. If I take every possible sample of size 38 from a population, do the sample means have to be normally distributed? Shit, yeah, that's the whole point. Right? Any sample can look like any freaking thing. I don't care how many freaking elements it's got, right? It can look like anything. If I take every sample of a certain size and plot it, greater than 30, it's going to be normal. Okay. Whoa, yeah. Okay. Kind of went to it. What tells me how wide or skinny this picture is? What tells me how wide or skinny?
Like the area?
No, area is always one. Standard deviation, right? That's the point of the standard deviation is it tells me how wide or skinny a distribution is. So if this standard deviation was 11, what would it look like if it was 1 instead? What would be different? Swooshed, right? It would be, right? It would all just be right there. You with me? Okay. So these are plots of sample means. And then they're going to make a normal curve if n is greater than 30. What if, instead, when I get the group of 38, instead of asking them to calculate their sample mean, their average age, I ask them to calculate their standard deviation, their sample standard deviation. Is everybody with me? It's a small change. right? They're all right there. They can calculate the standard deviation, right? Somehow I'm gonna show them how. You guys kind of with me? And I'm gonna plot all of those. Does that have to be normally just, in fact, what was it that told me the shape of these? Isn't it the standard deviation? So if I plot a bunch of standard deviations, do they have to look like this? No. In fact, I don't know what the hell that would look like. So that's what we're going to talk about. What would that look like? So the whole center limit theorem was all about plotting means we get from samples. Now we're talking about what if we plot all the freaking standard deviations? What the shit would that look like? Because it's normally the standard deviation that tells me how spread out the shit is, and that's what I'm plotting now. That's weird. Okay, maybe. So what it ends up looking like if you do this. And actually, let me do this. There's always a few different ways I could do this. What's a formula for like a z-score? Somebody give me one formula for a z-score. Anything, any formula for a z-score.
2 equals x minus b over the standard deviation.
Yeah, that's our most basic one, right?
Over root the n.
All right, so you can also do x bar minus the mean divided by the new spread, right? Or you can also do p hat minus p divided by square root of pq over n, blah, blah, blah. Do you see how there's multiple formulas? Don't they all fall in this picture? You know, as long as it's normal. You guys with me? So all of these different formulas all relate to the same kind of distribution. So, what if, instead of doing basically this, where we took sample means, and we can convert them into z-scores, all that kind of stuff, what if instead I took samples of size n, and I had people calculate their standard deviation, and then I plotted those, right? And now instead of plotting those, let me do this. I'm gonna kind of make a, sort of related to a z-score. I'm gonna do something, it's gonna look really weird, but too bad. All right, does any part of that look familiar? N minus 1, what's that? Degrees of freedom. What's S squared?
Variations.
Standard deviation.
Variance, sample variance. And what's sigma squared?
Standard deviation.
Population variance, right? You guys with me? So, if I have a population, and I know the standard deviation of the population, and I ask groups of size whatever to calculate their standard deviations, their own little S's, right, for their sample. If I calculate this, it ends up, let me ask you this, what's the smallest that a standard deviation can be? No? Can a standard deviation be negative?
Yeah.
Why would it be so weird? It would be so weird if a standard deviation was negative. What's the standard deviation for this data? You ready? 3, 3, 3, 3, 3, 3, 3, 3. What's the standard deviation? 0. Is everybody with me? Because the mean is 3. How far away do the data points get away from 3? 0 away. So standard deviation is 0. The minute I make any of them, if I made this 1, 3 become a 2, standard deviation is bigger than 0 now, right? Because now it's spread. If I made this 1 become a 4, it's still greater than 0. So the least it could be is 0. You guys with me? So this picture, unlike the normal curve that could actually go down to negative infinity, this is going to start at 0 always. It's going to look like this, and so I want somebody to help me figure out what's the official name for this kind of distribution. Skewed? Right. How do you always tell which way it's skewed? Which way did it look like somebody grabbed onto it and pulled it? Right? It's a big wad of taffy. You guys know taffy? Which way did somebody pull that sucker? That way. Right? And me, I always think of this as the Jabba the Hutt distribution, but you don't have to. Sorry. So it's a skewed right distribution. this is what it would look like if I asked groups of size whatever to calculate their standard deviation for their sample, and then did this to it. It would look like this. Look like this. Let me be more specific. Degrees of freedom greater than 1.
What was the question?
There was no question. I'm just telling you what that is. This, what do you think, here's the interesting, what do you think the most common, how do I say this? The most common standard deviation the most common sample variance I should get is the population variance, because that's the actual variance. Sort of like, if I take a sample, where should the sample mean be close to? It should be close to the real mean, right? Okay, maybe. So this should be close to n minus 1, where this sucker is. Okay. Good, I think it's enough for that. Let me give you this. So when we had the normal distribution, one of the first things I did was I gave you the z-score chart, right? And then we had the t-score chart, which is a little adjustment. Now we have the chart for this guy. Before I give this to you, let me give this an official name. So Z goes with z-score chart. This is called, you see how everything's squared here? So this is called chi-squared. This is the chi-squared distribution.
Do we have to write that so fancy like that?
Yeah. Well, if you don't, I'm not going to cry about it. But, it's supposed to be. Little props to the Greeks. We steal their stuff all the time. So chi-square, this, you cannot square root this away because it's just part of the notation. You understand? Chi-square equals 7 is not a problem to solve. Chi-squared is 7. You can't square root it. It's a part of the notation. You guys get what I'm saying? Sort of like f of x, you can't divide by f. Yeah.
What is the n and the 3 dots and actually again?
That was me just saying, take a sample of size n and make them calculate their sample standard deviation. That was me just saying a little story. We got enough of these. That would work.
I don't deserve it.
You don't deserve one. Well, Charlton, I'll have to post it up on Canvas so you can grab a copy.
Okay.
Well, that's.
I think a picture of it in the meantime. Okay.
Here, let me do this. So, guys, do you see anything on that chart that looks familiar? There should be a really obvious thing. Anything?
Degrees of freedom.
Oh, degrees of freedom. Okay. What's the z-score chart? When you look up a z-score on the z-score chart, what area does it tell you? The area that is to the left. And what does this chart say? Yeah, just because we want to be assholes. I'm gonna pull it up on the computer because I've run out of my own stuff. What's that? Oh, yeah. This does not break it down like that, no.
So you said on that chart right there on the board, it always starts at 0, so we're gonna be looking for whatever area is over the degrees of freedom. we're
Yeah.
looking for.
Which, say it again, sorry?
So like, the degrees of freedom are gonna be like that line you drew but erased, and we're kind of looking for the area to the right of it, right?
Here, we'll do an example. Shoot, I can't find it. Oh, here. Alright. This is chapter 11. Yeah, chapter 12 is linear correlation, chapter 11 is chi-square business. There we go. Alright, guys.
This one difference.
Is this, real quick, couple questions. Is this distribution symmetric?
No.
So if I were going to construct confidence intervals, now what can I use this to construct confidence intervals for? Standard deviations. So if I calculate, so what did we do with confidence intervals for? Didn't we take a sample, get an X bar, and then plus or minus some shit and say this is so certain that this interval catches the real mean, correct? So if I wanted to use this distribution to make confidence intervals, I would use it for standard deviations. So I would calculate an S, and that would add and subtract so much and say that the real sigma, I'm so much and so confident that this interval catches the real sigma, the real population standard deviation. Are you guys semi with me? What would be different here is, what is this? What is the absolute lowest this goes? Zero. And of course it goes theoretically forever, right? Never do that, by the way. Never put infinity on the number line. That drives me crazy. Go find it, pick it up, show it to me. So when we go to make confidence intervals, we're not going to get stuff like negative 1.645, 1.645. No, we're going to get stuff like 3.1876, 11.9734. Oh well. It's not symmetric, and it's not on either side of zero. Right? And your faces are all appropriately becoming more and more concerned. Yes?
So with that equation, the chi-squared equals the n-1, are we trying to figure out S, the standard deviation?
No, these are what we calculate. So I have a population, and I know its standard deviation, right? And then I can calculate, I can take one sample and calculate its standard deviation. So look. How do I use the z-score formula? What do I need to know before I can use it?
All of those components.
I need to know the population mean, and I need to know the population standard deviation for this version, right? And then I take a data point and I throw it in. Here, I need to know n, I need to know sigma, and then I go take a sample and I throw that in, and then I can calculate the chi-square. I can see where it falls on this picture. Okay, maybe. Now, let's see how to read this. If I want the chi-square, let's say that n is 11, and I want the chi-square that's got 0.025 here. Can you guys find that? Don't say anything. Can you guys find that on the chart? Don't say anything. So you got to worry about the degrees of freedom, right? What's the degrees of freedom? 10. And 0.025, is that to the right of what I want? Yes, to the right. So to the right, right? So 0.025, stop at 10. So we get,
2483.
where's it? Sorry, here's it. 20.483. You guys follow? So real quick, if I wanted to make a confidence interval, I would need the one that's got 0.025 on that side. Do you guys follow what I'm saying?
Yeah.
Go with me. And again, it's not going to be pretty. It's not going to be like negative 1.96 and 1.96. Oh, roses. No, it's not going to be that nice because it's not symmetric and it's not around zero and all that kind of shit. But real quick, if I want this chi-square, what area is to the right of it?
It's 1 minus that.
Good, 0.975, right? Let me say it again. This was easy. Why? Because I told you it's the area to the right. Are you guys all cool with the fact that if I want a confidence interval, these should be the same amount on each side, right? What confidence interval would this be? The 90, the 98, what confidence interval would this be? How much is outside? Total amount outside, 0.05. So how much is inside?
95.
So that's a 95% confidence interval.
Yeah.
Okay, big sigh, I like that. 0.025 is in there. Why? Because 0.025 is in there, and I want it to be equal on both sides to make a confidence interval, right? For this chart, it only understands areas to the right. So if I want that chi-square score, and normally when I do this, I call this chi-square big and chi-square small, right? Because that's the smaller one. What area am I gonna look up? 0.975. You guys see that? If that's 0.025, that must be 0.975.
So if that chi-square is 20.483, the one to the left is negative? No. Don't work out.
That's 0, so that can't be negative.
Yeah.
It's also not symmetric,
Don't work that way.
so we gotta look that shit up. So again, I'm sorry, yeah. Yeah. Say, I'm sorry, do it again. Say again. Yes, from 0 to this. From this on, yeah. So there are similarities. It's still, to make a confidence interval, I still chop. I still have the same amount on either side, right? It's just not symmetric in this case. Yeah.
Why did we stop at 10?
So the end was.
10. Oh, degrees of freedom was 10.
Oh, got it.
Yeah.
So how would you find the smaller one?
Let's do it. I want to. Degrees of freedom still 10. You guys agree with me? What am I looking up now? What area? What's 0.975? Notice something. Then we look here.
Yeah.
Notice how exactly,
The
You see
third
it?
one, third column.
Down one way out.
Yeah, good.
right? Here. 1, 2, 1, 2. Here, right? They are exactly across from each other. I don't know if you can see me. So
Yeah.
if I look at this one, it would be this one, this one, this one, this one, this one, right? It's kind of nice when I want to do chop confidence interval. Chop, it does exactly that on the chart, right? So I'm going to look at degrees of freedom 10, 0.975, 3.247.
So say right,
So that would be what I call chi-square small.
small.
What was it? 3.247.
So, but how would we know if we're looking, let's say, like, I guess on the right side? Or just, okay, like, you know, in the first one, it was, we know because you told us. There was that 0.25.
Yeah.
But then how do we know, like, what,
So-
if we're looking at that?
Here, when I did that, I didn't know I was gonna go all this way. So let's do this. Let's do a fresh one. What if I want, and by the way, that's just the first step in the problem, because in a confidence interval, when we find our z-scores, are we done? No, then we plug it into the formula, we go to town. Here, this is just like that step. We found our chi-square scores, then we'd have to plug it into whatever the equation is. And that would come later. Right now, I just want to make sure we can all read this chart correctly. So if I wanted to make a 98% confidence interval, right? Chop. Can anyone tell me how much is in each tail? Chop.
0.01.
0.01, correct? Yes? This is the easy one to look up. Why is this the easy one to look up? Because it's already to the right of the damn thing, yes? Let's say my sample size is 14, sure. So what's my degrees of freedom?
13.
Crazy. So 0.01, degrees of freedom 13. What do you get?
4.107.
Nope, right here.
Yeah.
0.01.
7.
0.01.
01, okay.
13.
27.688.
Yeah, 27.688. Kick ass.
27, yes.
Now watch this. 27.688, right?
4.107.
Yeah, 4.107. See?
Okay.
You really don't have to do that work we did at first. You can if you want to. If that's 0.01, what's this?
0.01.
No, if that's 0.01, what's everything else?
0.99.
0.99, so it ended up looking there, right? But if I just go, all right, I'm here, let me go to the equal place there, got it. Okay, and again, that's a little anticlimactic because that's just the first step. That's just like finding z-scores, right? It's just like finding 1.645. Don't you have to then do all the actual work? You know, like, oh, that's great, Jeff. You're making us feel so much better. Okay. So again, I just want to make sure that we can all read this chart correctly. What's up? You gonna be all right? Again, how long have you been working with chi-square distributions? Yeah. All right. Give yourself a break. Yeah.
What's the twist?
What's the twist?
Yeah.
I'm not M. Night Shyamalan.
This is it?
The lady came for the lake. No, I don't have a twist. They don't like water. They're demons. No.
So then, so then that, the 4.07,
4.107?
yeah, is that from as soon as?
So that would be this one here.
From the first line.
Okay.
Covering all the way to hit the 27?
So from
Like-
4.107 chi-squared to 27.688 chi-squared,
Right.
there's 98% of the data. That's why it would be a 98% confidence interval, right?
Okay, just because when you say 98, like that's all 98's in the middle, right?
Totally.
Okay.
Because there's
So
1% on either side, so it must be
so-
98% inside.
So then that 4.7, wouldn't that also be like if is it wrong if I put it in the middle, not in the beginning
Put
of it?
this in the middle? Yeah, it would be
And
wrong.
then-
It's sort of like, all right, 95% confidence interval. Doesn't that go from negative 1.96 to 1.96? Right?
Mhm.
What's in the middle? If I put that in the middle, would that be good? It wouldn't make any sense.
Yeah.
Okay, same thing. It's just that this isn't symmetric. So we gotta kind of let go of, this was really nice. You guys didn't even know how nice this was, that once you get one, you know the other. This shit, oh shit, I gotta find one, then I gotta go find the other one. Because it's not symmetric. I can't do that shortcut. Okay. Yes.
So we're just solving for those, like, the x's, not like the middle portion?
So, again, if I'm gonna make a confidence interval, we're not gonna do that right now, but I just sort of got here. This would be the first step. It's sort of like finding the z-scores, 1.96 and negative 1.96. Wouldn't the next step be to throw those into the formula? All right, we just did that step. We just found the chi-squared. Then we'd have to throw those into the formula and get the confidence interval. Does that make sense?
Yeah.
Okay, good. All right, so what we're gonna do tonight is we're gonna do something a little different. Yeah, we'll turn this off for now. Oh, I almost forgot. Look at the degree of freedom 1. Look underneath the point, let me see,
0.995.
under the point 1. Do you see it says 2.706?
Mhm.
Okay, can somebody real quick, guys, can somebody just take the square root of that? Just take the square root of 2.706. Does everybody see that number on the chi-square chart? I'm not just making that shit up.
7.32.
No, take the square root.
1.644.
So 1.645, yes?
Yeah.
Does that sound familiar? What's the next number over? 3.841, take the square root of that. 1.96, does that sound familiar? So, what a chi-square is, on one level, is we take a normal curve and we fold it on itself. So the z-scores overlap and they square each other, right? So really quickly, 1.645, that was the square root of 2.706, yes? And that related to 0.10, alpha 0.10. Stay with it, guys.
1.6 for 5. Does anyone remember what confidence interval that was for?
95?
90%. So when I fold it, this is 5 and this is 5, 10. So another reason pi has a square on it is because it's actually, for degree of freedom of 1, it's the square of z-scores. All those are squares of the appropriate z-scores. The higher levels of degrees of freedom are what let us do what we're about to do. We can analyze things that we could not analyze with a normal distribution. So here's the kind of problem we're going to focus on now. So let's say, for some reason, somebody believes that the grades in across an entire population of a certain class, let's say all the stats classes, they believe that all stats classes should have grades that follow this distribution. They believe that 10% of the grades should be A's, 25% should be B's, 30% should be C's. Okay, now I gotta be careful. Where is this with that? Let's do 25%. I don't want to make it. Yeah, sure, why not? 25% for D's, and that should leave 10. Is that right? 50, 80, 90. Yes. So a claim has been made. I want everybody to calm down. We're not going to do a full hypothesis. Calm down. We're going to be okay. Right? I'm not going to make this into a hypothesis. I could, but I'm not. You guys all with me? This is somebody's making a claim. I think that the grades should follow this distribution. Have you guys? Yeah, I think on the first day you even said this. You guys have heard of the bell curve in relation to education. In fact, when I say I curve the grades, I literally picked it up and I moved the damn curve, right? And so I also make it go. So not only do I move the mean up a little bit, I also shrink it. Right, so that's what it means when I say curve the grades. So they've got an idea of how grades should be spread out, right? How could we check this? How could we test this claim?
You put the percentages and then listing of actual averages.
Yeah, let's take a sample of a certain number of stat students and get their grades, right? Let's say that we're actually researchers at the college, so we actually have access to this data. So let's say we take 200, sounds like a good size, yeah? 200 students, stat students, and we look at their final grades. Can anyone tell me, here, make a table, leave this first one blank for now. Put an E here, okay. That's gonna stand for expected. How many A's would we expect if we are this person? How many A's would I expect? 10%. 10% of what? 200. So what's 10% of 200?
20.
I would expect 20 A's. Does everybody see what just happened? So I have a claim about how data will be distributed amongst certain categories, right? In this case, the categories happen to be grade levels, grades, right? How many B's would we expect? 50. How many C's? 60. And the nice thing is I made it symmetric right here. So this would also be 50 and this would also be 20. Oh. Now, somebody said, I think I heard something in the right direction. To test this claim, well, how do we test any claim? So he makes a claim. What do we immediately go do? Take a sample. So we took a sample of 200. Those are what we expect. Now, is that the actual number of A's? No, this is what we would expect. And then we go look at the actual data. Let's say that there were 16 A's, 45 B's. Oh, shit, I'm gonna make this work. 67 C's, I don't know, flipping hell. 51 D's, what do I have left? Let's see. 61, 128, 179, so that should be 21, I think. Is that right? Somebody help me out.
Yeah.
Yay, math, okay.
Those are the actual values? you
Yeah,
said?
so we call these the observed values, that's crazy.
Oh.
O is observed, E is expected. O is actual, E is theoretical. Dude. Real quick, what's the immediate thing you would do if the question is how far off was my expectation? You would subtract the damn things, right? Do you remember what we did though when we calculated standard deviation? And we subtracted shit, and we're like, oh shit, adds up to be 0 and stuff. So then we square it, right? Yeah, I don't know. You guys are all like, I don't know, dude.
So how'd you get the observed values again?
Oh. I actually have to go look. And since I didn't have 200 grades, we just made shit. So we're pretending like we had a list of grades and we saw 16 of them were A's, right? So I would give you these numbers. These you would come up with yourself based on the claim I would give you, right? Okay. How are you feeling so far? The math involved, not very deep. The concept behind it, so here I'm going to do this. I'm going to take the difference and I'm going to square it. Because it shouldn't matter. If the question is how far off was my guess, it shouldn't matter if it was up or down. Both of those should count against me, correct? So I want to square them so the negatives don't end up taken away from how wrong I was. So help me out. We can do this, can't we?
16.
Negative 4 squared, 16. 5, negative 5 squared, 25.
49.
7 squared, 49. 1 squared, 1. 1 squared, 1. Now, if you were guessing the price of something, right? And it actually costs $2, and you guessed 90 cents. How much off were you? $1.10, right? But relatively, were you pretty far off?
Yeah.
You were less, you guessed less than half of what it actually was. Do you guys kind of follow? So that $1.10 is relatively significant. Do you agree with me? Sort of this, I could say the same thing, like if I had 90 cents and I found $1, would that be significant to me? If all I had in the world was 90 cents and I found $1,
Yeah.
that would be, if I'm Bill Gates and I find $1, I maybe was gonna scrape something out of my shoe on it or something, right? No, he would pick it up, because that's why he's a billionaire. Alright, you guys kind of, okay. What the shit does that mean, Jeff? So if what did I say? It's actually $2, and I guess $1.90. So I'm off by $1.10, yes? That's a lot, relatively. What if if I guess $9 billion, and the actual price is $9 billion and 1.10 cents. Do you understand what I'm saying? So I'm off by $1.10. Would you say I'm off by relatively a lot?
No.
No. Somebody's like, guess how much is this? 9 billion. It's actually 9 billion and $1.10. It's like, no, 9 billion. Shut up. But if they say guess this, and I'm like 90 cents. It's actually $2. You're way off. It's still, they're both $1.10, correct? Mm-hmm. Okay. So how does that relate to this, Jeff? It doesn't. I'm joking. I need to divide this by what I expected it to be to get a relative difference, right? So the last step in this table, just to let you know, so you know how long this is. I'm going to take observed minus expected squared divided by expected. So somebody help me out. Well, 16 divided by 20, that's not hard. 0.8. 25 divided by 50 is definitely not hard. 49 divided by 60, that might be a little harder. Give me a minute, wait. 80, 80, something, 81.6.
81.6.
Yeah. 0.816, right?
Oh, yeah.
So 0.82, that's done. Woo!
1 divided by 50 is 0.02. 1 divided by 20 is 0.05. Is that cool? Okay. If I add all those up, that captures all my errors. That gives me an overall amount that I'm off by relative to how big the numbers are. I love you guys. Some of you guys have very pained expressions. Creating this table, is it very intensive?
No.
I'm going to tell you these. I'm going to give you what you need to figure these out, and then you just do that shit to it, right? I want you to understand the idea behind what we're doing. Who had a hand up? Somebody? Yeah.
So when does the equation come in?
It's coming. You ready? And this is going to be a different equation. I think I told you guys that. So what do I get when I add all these up? Somebody help me out. 2.12. 2.19, I think. Is it? Neato. That is another equation for chi-squared, this last group. This is just like where'd they go? They're gone, Jeff. You erased it. Just like there was z equals x minus mu over sigma, there's z equals p hat minus p over square root of pq, all that kind of shit. They all meant the same thing. Didn't they all mean z-scores? So, what we just did, that needs to move. What we just did is another formula for chi-squared. It also falls in the same exact distribution. I don't need this guy. So the most fundamental definition for chi-squared is n minus 1 times s squared divided by sigma squared. Sort of like z equals x minus mu divided by standard deviation. That's the first z-score formula we learned. Then we learned all these other ones, and they all fall back into the same distribution. Same idea here. We have that chi-square, and we have that chi-square. So, the one thing we're missing, we calculated what would have been equivalent to z star in a hypothesis test. Isn't this from our sample? Did we calculate this based on our sample?
Yeah.
Totally. So that is kind of like our z star would have been. Right? Did I tell us, sounds good. Did I tell us what alpha is? What do you assume anytime I don't tell you? 105, good. Now real quick, what do you think the degrees of freedom are? And you're gonna get it wrong. It's okay, because I didn't tell you yet. What would you think the degrees of freedom are? 199, okay. In this kind of test, how many categories are there? 5. And don't, I mean, who the shit would know? Who the shit would know? So you're fine. Degrees of freedom then for this kind of test would be categories minus 1. And you're gonna love this. You ready? Categories minus 1, yes? So categories of start with the letter K. I don't know why we use the K, we just do. We use the K. So in this case, it's K minus 1. So in this case, the degrees of freedom would be 4. So take a minute, don't say anything. Can you find the rejection region chi-squared? Alpha 0.05 to the right, degrees of freedom is 4.
9.488.
Say again, sorry.
9.488.
9.488. Is that what you guys get? Sounds about right. Can't remember. Okay. So if my prediction had been perfect, if my expected was perfect, then these would have been all the same. Do you guys agree? What would all of these numbers have been then? If these are the same, these numbers would have been 0, right? Because the difference of these would have been 0. So if my expectation lined up perfectly with reality, which barely ever happens, the differences would have all been 0, the squares would have been 0, divided by e would have been 0. You guys with
Where's that 9.488 from?
chi-square table. from the chi-square table.
What are you looking at?
Oh,
though?
the thing you didn't get. Sorry.
Oh,
Yeah.
and how do you find it?
Here, let me do it again.
You're just doing 0.05 and then 4 degrees of freedom?
Yeah, that's it.
Okay.
Okay, good. Now that it's on, let's see. So 0.05, 4 degrees of freedom. There's your 9488. Yeah.
Now, real quick, I want to explain why it's where it is.
But
Don't you dare.
isn't that pi,
Say again?
is that little x, or is pi not the x?
Sorry?
Isn't 9.488, doesn't that equal pi?
In a hypothesis test, don't we have a z-score for our rejection region? Don't we have a z-score for the rejection region?
Yes.
Yes. Don't we also calculate a z-score from our sample?
Okay.
Yes. Well, I call it z star to make sure, because there's two z's, just to make it really clear. Here, we have a chi-square from our data. That's like chi-square star, but there's already a square up there. I don't want to make it all cluttered. You can make a chi-square star if you want to, right? Then I need a chi-square that tells me how far enough away is. So if my prediction had been perfect, we would have ended up with 0. Does everybody agree? Because there would have been no difference between prediction and expected. Yeah, I mean prediction and observed. So not only do I need it to be not 0 to show evidence that there is a difference. Stay with me now. So let's say that there really is not a difference. Couldn't I take a sample that just because of sample variability, I do get what seems to be a difference? So just like with hypothesis tests, not only should it be different from what it claims, it has to be different enough from what it claims. So here we're fighting against the claim that there is no difference. We're trying to find evidence against that. So if I make it in here, that is evidence that the grades don't follow this. Yes?
So is the 9.488 the expected price?
No, this is my rejection region. This is just like 1.96, 2.575, right? The z-score you would look up for your rejection region.
You don't look at the opposite, which, you know how, like.
No, because we're not doing a confidence interval.
Looking for everything outside.
Yeah. So the kind of test this is called a goodness of fit test. This is called a goodness of fit test. That is not my name for it. That is the name for it. So it tests how good the fit is between expectation and reality. Right? So I guess that day they were tired, like, goodness fit. Yeah, okay. And they wrote it down. So it became the name. Did we make it far enough away? How far did we make it? So we're like there, maybe. Did we make it far enough away? No. So I really want you to understand. If my observations and my expected were perfectly the same, I would have gotten a 0. That would definitely not have been evidence there's a difference, because if there were no difference, I would expect to see no differences, right? So not only do I have to be not 0, I have to be far enough away from 0 to account for sample variability. The exact same thing that happens with hypothesis tests. That's why if somebody said, I think it's 10, and you're like, I got 10.1. Well, how relatively far away is that? Is that far enough away to show evidence it's not 10?
Okay, you say it's not far away, right?
Nope.
But then, okay.
From 0.
From 0. Not 0 from the 9.4.
No.
Okay.
So this is how far away from 0 I need to get to show evidence that it's different. We didn't get far enough away. So did we find evidence to show that the grades don't follow this? No. We have not found evidence that the actual grades don't follow this. Okay, I like it. Yes.
So that 9.488, that's kind of like the z-score, or is that the area?
Rejection region. Rejection region.
It's not
So
the area?
the z-score in the rejection region. The area is 0.05, right?
Oh.
The area in there is 0.05, and that's what led to this. Okay. I like it. So let me do this. Let's now look at my horrible writing. Let's look at a computer-generated thing. Give you this worksheet. See if you got enough.
You don't make us write a conclusion.
Not a very extensive one. So in this one, I'll show you what the conclusion would be.
Because we didn't talk about what the whole or the hall was, right?
We're not gonna do a full IMOS. We could. Alright, so let's take a look. There we go. I gave you, the first example is the other type of problem we could see. So you could either see a problem where they tell me exactly what percentage would show up in each category. Yeah?
Just real quick, is this, chapter 12 or 11?
11. 12 is correlation. 11 is chi-square business.
So we should be able to finish all of chapter 12 or we're finished. Is this right?
Yeah, we did all of 12. So the difference. So the second problem one here is just like the one we did. You guys see that? So I tell you the percentage I expect. The first problem, what is the thing we're testing? What's kind of like the claim we're testing here?
If all of the colors,
The number of
if the
colored
colors of
M&Ms
all
in each
bags
bag.
are uniform.
Uniformly distributed. So what does uniformly distributed mean?
The same.
Everything should get the same. So if there's 42 total, answer life, universe, everything, 42 total M&Ms, how many categories do I have? 6. So how much should each get? 42 divided by 6. So there's only 2 types of goodness of fit problems. I'll give you a percentage distribution, and then you just take 10% of 200, whatever, right? Or I just say, we think it's uniformly distributed, in which case, you just divide the total by how many categories. That tells you how much each category gets. How are we doing so far? Okay. So, in this problem, I did everything the same way, right? You could even see, I'm going to show you on the next problem, I'll do it in the calculator, so you can do L1, L2. This would be L1 minus L2 squared. So you can actually do it in the lists if you want to. So what I want you guys to do, because you're all experts now, do what you can. I want you to do number 2. Feel free to work together. If you need a calculator, come up